welcome to the fourth lesson in our series on electromagnetism. In our first three lessons, we explored Ooster's discovery that showed one link between magnetism and electricity. He showed that when a current passes through a conductor, a magnetic field is created at 90 degrees to the direction of the current. It was not long after this discovery that Ampere showed that two current-carrying conductors placed close to each other will either repel or attract each other in just the same way that two magnets will. This showed that because of the magnetic fields around them, there is a force between the two current-carrying conductors. Michael Faraday realized that there is a link between electricity, magnetism, and a force which can be harnessed to do work. He applied this idea to design a simple electric motor. You will find electric motors in almost all appliances we use today in our homes and in industry. The invention of the electric motor was not, however, Faraday's greatest achievement. He was really curious about the relationship between electricity and magnetism. He knew that electric current produced a magnetic field and wondered if a magnet could be used to produce an electric current. At the time, Faraday was a laboratory assistant and spent most of his time doing experiments. He was eager to find a new way to generate electricity because the chemical cells he used in the lab were not always a reliable source of electricity. He began his investigation by placing magnets of different strengths near different sized coils, but each time he set up an experiment, he was unable to detect a current in the coil. Although at times he was discouraged, he never gave up. The breakthrough came one day when he moved a magnet inside a coil and detected a current in the coil. In today's lesson, we will focus on this famous discovery Faraday made and analyze the law he used to explain his discovery. By the end of this lesson, you should be able to explain what happens when a bar magnet is pushed into or pulled out of a coil, state Faraday's law, and use this law to solve problems. Now, before we set up an experiment similar to the one Faraday did, there is one idea I want to recap from the work you have done on electric current. Do you remember the term EMF? It stands for the electromotive force. Scientists today think of it as a measure of the total electrical potential energy per unit charge available in a battery or source of electricity. EMF is measured in volts and in some cases is in fact equal to potential difference. A galvanometer can be used to measure the EMF or potential difference across the ends of a conductor. Here is a metal conductor connected to a light bulb in series. A galvanometer is connected in parallel to the conductor and the light bulb. The reading on the galvanometer is 0. This means that there is no EMF across the circuit, and we can see that no current passes through it since the light bulb did not light up. Now, when I connect a battery of cells to the circuit, the needle of the galvanometer will move. Let's see how. Showing that there is a potential difference across the circuit. The bulb lights up, showing that there is now a current passing through the circuit. In this circuit, the battery was the source of the EMF. It is important to remember that without a potential difference or EMF applied to the ends of a conductor, there will be no current in the conductor. Knowing this, we can now move on to doing Faraday's experiment. Here is a coil of insulated copper wire. You can see that there are many loops in this coil, and they are wound together very closely. The coil is connected to a center zero galvanometer. I'm going to push the north pole end of a strong magnet into the coil. Observe what happens to the needle of the galvanometer. The needle of the center zero galvanometer moves to the right, and then it comes back to zero again. And look, when the magnet is pulled out of the coil, the needle jumps in the other direction, and then it comes back to zero again. And if the magnet is pushed in and pulled out and pushed in and pushed out, we can make the needle of the center zero galvanometer vibrate from side to side. What can you deduce from the fact that the needle of the galvanometer moved? The moving needle tells us that an EMF has been detected by the galvanometer across the ends of the coil. So current has moved through the coil. Look carefully again at the apparatus. We have only a magnet and a coil and a galvanometer with some connecting leads. There is no battery here. So what is the source of the EMF? Well, it is the movement of the magnet in the coil that created the EMF. Only when the magnet moved was an EMF detected and electricity generated. Michael Faraday used the term electromagnetic induction for the process of generating electricity by moving a magnet in a coil. The EMF produced by a moving magnet in a coil is called the induced EMF, and the resulting current is called the induced current. Let's investigate what happens to the induced EMF when we change the motion of the magnet. For this experiment, I have swapped the galvanometer with a voltage sensor so that we can record and compare the size of the induced EMF for each of our experiments. The sensor is linked to an Explorer data logger, and the graph will be shown on the laptop screen. Watch carefully what happens. First, I'll push the north pole of the bar magnet into the coil slowly and then stop. Look at the readings of EMF I have for this time. The voltage sensor registered a small positive EMF while the magnet was moving, but then returned to 0 volts when the magnet stopped moving. Now I'm going to push the north pole of the bar magnet into the coil very quickly. Watch what happens to the EMF readings. Once again, the voltage sensor registered a positive EMF in the coil, but this time the value was much greater. What conclusion can you make based on this evidence? I think it shows that when the magnet moves faster in the coil, the induced EMF is greater. Faraday found that there is another way of inducing an EMF in a coil. Instead of moving the magnet, move the coil and keep the magnet fixed in position. Watch what happens. The voltage sensor registered an induced EMF when the coil moved over the magnet. This shows exactly what Michael Faraday discovered. We can say that whenever you move a magnetic field relative to a coil, an EMF will be induced in the coil. It does not matter if the coil moves or if the magnet moves. What matters is relative motion between the coil and the magnet. From his experiments, Faraday developed a theory to explain why an EMF is induced in a coil when there is relative motion between a coil and a magnet. His explanation has become known as Faraday's law of electromagnetic induction. Have a careful look at this statement of his law. the magnitude of the induced EMF in a conductor is directly proportional to the rate of change of magnetic flux through the conductor. For a given coil, we can write a mathematical expression for Faraday's law as follows. E is directly proportional to delta phi divided by delta T. Let's look at what all these letters and symbols stand for. E stands for the magnitude or size of the induced EMF, and delta phi over delta T is the rate of change in magnetic flux. Remember that the magnetic flux phi is equal to the product of the magnetic field B and the cross-sectional area A through which the field passes. So why did Faraday link the size of the induced EMF to the rate of change of magnetic flux? To understand this, let's think back to Faraday's original experiment when he placed a stationary magnet inside a coil. The magnetic field lines from the bar magnet cut across the area of the coil, so there is a magnetic flux cutting through the coil. But notice that there is no induced EMF in the coil. There is no reading on the galvanometer. Watch what happens when a magnet moves relative to the coil. When the magnet enters the coil, the field lines only cut through a small area of the coil, meaning that there is a small magnetic flux cutting through the coil. But as the magnet moves further into the coil, the area increases, which means that the magnetic flux has increased. So there has been a change in magnetic flux. This change in magnetic flux occurred during a certain time interval while the magnet moved. A change in magnetic flux per unit time is called the rate of change of magnetic flux. If we move the same magnet faster in the coil, the change in magnetic flux will be the same as when the magnet moves slowly, but the time taken for this change will be less, and so the rate of change will be greater. Remember, when the magnet moved slowly in the coil, the induced EMF was smaller than when the same magnet moved quickly in the coil. So that's why Faraday concluded that the rate of change in magnetic flux is directly proportional to the magnitude of the EMF induced in the coil. We can expand this expression as follows. Now, looking at this expression of Faraday's law, can you suggest any other factors that will affect the induced EMF? Can you see that the magnetic flux is dependent on the strength of the magnetic field B? If we make the magnet stronger, we will increase the magnetic field. Because a stronger magnet will have more field lines, it will cut through a larger area on the conductor than a weak magnet. The result of using a stronger magnet with more field lines is a greater change in magnetic flux when it moves relative to the coil. Also, a greater EMF should be induced in the coil than when a weaker magnet moves. Let's test this idea by measuring the EMF induced by a strong and a weak magnet moving into the same coil at the same speed. We will do this by dropping the two magnets through the coil from the same height. Your job is to watch the reading on the voltage sensor to see if there is a difference in the EMF. Can you see that the stronger magnet induced a bigger EMF in the coil? This experiment confirms the relationship between B, the magnetic field, and the magnitude of the induced EMF, as shown in Faraday's law, which can be written like this. Faraday found that another way to increase the induced EMF is to increase the number of loops or turns in the coil. Let's test this experimentally. Here is another coil of the same length as the previous one, but this one has less turns. It has 240 turns. And when I drop the magnet through this coil, you will be able to see that I get a maximum reading on the voltage sensor that is smaller than the first one. What conclusions can we draw from this experiment? We have confirmed that the number of turns in a coil is related to the size of the EMF induced in the coil. In this experiment, we have moved the same magnet through the two different coils in the same amount of time, so the rate of change of magnetic flux passing through each coil is the same in both coils. In this experiment, the rate of change of magnetic flux is a constant. We can therefore state that the size of the induced EMF is directly proportional to the number of turns N. These experiments have confirmed different types of relationships for induced EMF in a coil. Now we can combine the two relationships we have found and write an equation for Faraday's law as follows. E is equal to N times delta phi divided by delta T. E stands for the magnitude of the induced EMF, N the number of turns in the coil, and delta phi over delta T is the rate of the change in magnetic flux. Remember that the magnetic flux phi is equal to the product of the magnetic field B and the cross-sectional area A through which the field passes. This equation can be used to calculate the magnitude of the EMF induced in a coil. I want you to use the equation to solve the problem in your task for today. Here are two different situations. A magnet with a magnetic field of 0,1 Tesla takes 0,1 seconds to move through a coil with 120 turns. A magnet with a magnetic field of 1,1 Tesla takes 1,5 seconds to move through a coil with 200 turns. The coils are both the same shape and length. The cross-section area through which the magnetic field passes is 1 meter square in both coils. Calculate the magnitude of the induced EMF in each coil to find which is greater. In our next lesson, we will show how the relative motion of the magnetic field is related to the current induced in the coil. See you then.
Yeah.